Hi, welcome to this video. I'd like to talk about one aspect related to graph problems. So at our last practice, we had a number of problems. Among the problems, it's called "Where's my internet?" and I thought it was a really easy problem. But a number of you struggled, and so it shows requires some basic techniques dealing with graphs. Okay, so this is a problem that if you're more experienced, that's a problem that you just do like this, right, in 3 minutes. But if you don't know the trick, then it takes a little bit longer. So let's take a look at this problem. Okay, so in this problem, the problem that was given is a graph. Okay, so for example, this graph here was given as um, in the first example input here, we have a graph that consists of 6 nodes, and these nodes are 1, and then 2, and 3, and 4, and also node 5 and node 6. And the edges in this graph are between 1 and 2, 2 and 3, 3 and 4, and 5 and 6. And the question was, which are the nodes that you can reach from node number 1? And in this case, the answer would be 1, 2, 3, 4. So you cannot reach 5 and 6. And this is what the program asks you to output. If the graph is like this, just node 1 and just node 2, then like here, the entire graph is connected. And then other examples. So this is what we call graph connectivity. Okay. All right. So what do we need to do in order to be successful at solving these types of problems? Okay. So first of all, we need to be able to represent graphs. Okay. Now, in order to represent graphs, there are two basic ways. Okay, so generally when you have a graph has nodes, right? Let's say this is node number, maybe node number 2, and this here is node number 3, and the two are connected, right? So the question, how do we represent this? The first thing is we need to have some way of representing those nodes itself, right? And in a programming contest problem, these nodes could represent anything, something in the problem, maybe cities or maybe some kind of states that come about when you traverse a problem space. But in many cases, the best way to represent those nodes is simply by numbers. And here in this case, we are given n, which is the number of nodes in that graph, is up to 200,000. And so we number the nodes in the graph with numbers. So typically we start with 0, 0, 1, 2, 3, all the way to n minus 1. So in this particular input, we needed to translate the input, which was 1 based. We would probably subtract 1 to make it 0 based. So then we need to represent this graph here. Okay, so we need to represent this edge, and there are two ways. Okay, so one way is referred to as an adjacency matrix, where we create a table and we have a Boolean flag 0, 1, and that says whether two particular nodes are connected or not. But here we're using something else. We're using something called adjacency lists. And in fact, I would say probably in 80% of the problems in programming contests, we are using adjacency adjacency lists. Okay. Now, why are they called adjacency lists? Because they record for each node its neighbors. The neighbors are those nodes that are adjacent to it. So for example, in this case here, to record that 2 and 3 are neighbors, we are recording that 3 is a neighbor of 2 and that 2 is a neighbor of 3. So we have an array of lists, one for each node. So this is the first one, the second one, and so on. And so in this case, in this array here, we would have these lists. And so for number 2 in that list, we would have node number 3 that says 3 is a neighbor of 2. Similarly, 2 is a neighbor of 3, so we would have that entry here. Now suppose we had another node here, let's say node number 4, and that's connected to number 3. Well, in this case, node number 4 would have a list that says that 3 is its neighbor. And 3 also would have another neighbor here, okay, 4. I'm drawing, so these are these adjacency lists. I'm drawing these like lists, kind of like, with arrows. But in practice, as we'll see, we use data structures that are more array-based in this case. So this is the basic idea. Okay, the very first step here before we can go about solving this problem is to understand how these graphs are being represented. Okay, and let me just go ahead and see if we can code this. Okay, right. Okay, so I'm going to write a program. I'm going to use Java here because I think that that most of you are familiar with, or um, can pick up. I'm gonna write this in Vim because that's what I'm familiar with. I usually import Java util star for a programming contest. Some of you may have an IDE where this is all something that you can copy and paste from. I'm going to just type it in. The very first thing is we need an input device. We typically use a scanner, but we'll see what happens here in this case. We use the scanner. The first element, the input, was the number of the nodes. There was and the second one was the number of edges here in this case. Right. So um, let me erase this here. Do that. Okay. So so the number of edges, and then the next part is, so now we need to represent these lists. Okay, so the way to represent these lists in Java, when the number of nodes is given, is as an array of lists. So these lists contain integers, okay, it's capital integers, and I always call them adjacency, okay. Now, this array needs to be initialized, and how many elements are in it? N, because I'm using from 0 to n minus 1. Whenever I write this, the very next thing is I put in here a suppress warnings unchecked, because I don't like compiler warnings in this case. So now these adjacency lists, they all have not been initialized. None of them have, so we need to initialize them because this is Java, and if things are not initialized, then we get a null pointer error. So I'm going to initialize it here in this case. All right, so now we're ready to read in the data, and there will be m lines, and in each of these lines, there is going to be two integer numbers that are the nodes that are being connected. I'm going to call them A, and I'm going to call them B. And so now we need to add B to A's list and A to B's list. Okay, and the way we do this is we say correct for the indexing, and we're going to add this with here, and we're going to do the opposite as well, and adding A to B. So now if you have a graph, and then one of the nice things about Java is that we can actually output to the screen that this works. So let's try that. Okay, so the adjacency list arrays you can output to the screen. So let's test this. Okay, so we have the program, and I'm going to run it, and I'm going to copy and paste one of the test sets. So I'll put this one here. Okay, so if I copied this one in here, I'm sorry, that was a glitch with my computer's copy and paste mechanism. So if I copy this in here, we see for this particular graph, we see the output. Let's see if we can read this here. Okay, so in this graph um, we had node number 0. Okay, its neighbor here is 1. Node number 1's neighbor is 0 and 2. Let's see. So we have node number 0 here. This is this one. And its neighbor is node number 1, just this one. Okay. So we go from here to there. It's really we're going from here to there and from here to there. So this is what these things say. And then we have one's neighbor is number 2. And so this is this part here. And so now similarly here, number 2. So this is 0, 1, 2, 3, 4, 5. So 2 here is connected to node number 3, 3 is only connected to 2, and then 4 and 5 here are connected to each other, right? So we can verify, and with some practice, you're going to get really fluent at that, looking at this output here to see that this is in fact the input that's given in the problem. Yeah. All right. So let me erase this, and so we now have the graph read in, and we can start on actually solving the problem. Okay. So now to solve this problem, I like to output this to system.error. This way, if I forget to comment it out, it won't affect the judging. So now we need to traverse this graph. Okay, so we need to have some way to go through this graph and see what can we reach in this case here from node number, from the first node, right, which is 0 numbered in this, but it's 1 numbered in the problem. So to do that, we can use a number of graph traversal algorithms. So I'm going to show something called DFS, or depth first search, that I like to use. I'm going to show you the non-recursive form and the recursive form. So to do that, we need to do a little bit of bookkeeping. First of all, we need to remember which of the nodes we've been to. Okay, now to do that, we exploit the fact that those nodes are numbered as numbers, right? So all we need to say, have I been here, is a Boolean array. And usually it's called something like visited or marked, or, have I been here? How about we call it marked? Okay. So this array needs to hold n booleans because there are n possible nodes where we could have been. And since we start from node number 0, we set the first one to true. Now we also need to keep track of those nodes that we have been to, but where we haven't fully explored their neighbors, right? Because the idea will be to go to one node, see what neighbors we can go to, and so on until we run out of new nodes to visit. And to do that, we need a data structure. And this data structure, we could use a stack, we can use a queue. For DFS, we would use a stack. But what I always use, and a lot of programmers use, is a DAG, because a DAG can be used as either, and it performs pretty well. I like to call it DFS, and so I make that here a DAG. And then so in that DAG, we can push number 0 in it. So this says, okay, we start from number 0, and this is the first thing in there. Now the algorithm now will be a while loop. So while this this queue is not empty, okay, right? So while it's not empty, we do the following, okay. So we grab a node, and I always call it u, from that queue with pop, and now we need to explore its neighbors, okay. And so now, because we arranged them into an array of lists, we can just say int v, and so what the adjacency list that belongs to you. So this will be the neighbor, and we say, well, what if we have visited that neighbor already? Well, then we don't have to do anything. But if we haven't visited it, then in this case, we will need to visit it. And we do that by, first of all, making a note that we've done that, and then by adding it to that particular queue. And this is our entire DFS, actually. So when we're here at this point, the marked array, those entries that are true are the nodes we were able to visit, and those that aren't are not. Now the problem asks us to output connected if all of them are reachable. So to facilitate that, let's keep track of a counter that says how many are left to connect, which is all but the first one. And so that counter would then be decremented here. Now, if none of the nodes are left, so if this is 0, then we're going to output we are going to output, I think, connected here. But otherwise, it wants us to output those nodes that have not been connected, and it wants us to do so in the order in which they are listed. Okay, so let's do that here by going from 1 to n. And then in this case, so if a node is not marked, right, not marked means it was not reachable, then we're going to output that node's number. And here on output, this is where I correct for the off by 1 issue, but the shift by 1. Okay, so this would be the code. Let's see if that actually works. Okay, so we get the output 5 and 6 in this case, although, um, yeah, we get the output 5 and 6. Okay, I removed the code that offers them, that echoes back. Now let's try the other case. Then the other case was 1, 2, and 1, 2. No, actually it was 2, 1 and 2, 1. That works similarly. 2, 1 and 1, 2 would work as well. And then the this output here is 2, 3, 4. So it appears to work. Now let's see if we can what happens if we submit this to the system here. Let's do that. So let's say submit. Um, all right. So we submit this, and it starts running. Well, it looks pretty good. Each check mark is a test case, and it runs, and runs. But let's see what happens at the end. Okay, so here, bang. So this failed. Why? Time limit exceeded. Um, this has nothing to do with the graph traversal. This has to do with Java being slow. And specifically here, we have to think about what's the worst case input. The worst case input involves up to 200,000 lines. And in fact, the worst case output also involves up to 200,000 lines. And for scenarios like this, um, the use of Java scanner is just too slow. Okay. Unfortunately, this is a problem that we've recognized, and we have code in our handbook that will fix that. And I'm gonna just pull up that code. You have access to that as well. And that code is called a fast scanner. Okay, so in this case here, what I'm going to do is I'm going to copy and I'm going to paste this fast scanner into the code. And now it's called a scanner class, and it almost acts like Java util scanner. The only difference is it doesn't take an argument. So I'm just going to remove this argument here, and I'm going to find that it doesn't work. The reason it doesn't work because it requires Java IO. So I'm going to compile this, and then I will be on my way to resubmitting this program, and let's see what it does this time. So it compiles, it runs. Audio looks much faster, doesn't it? Let's see if it makes it all the way. Okay, it still does not make it all the way. Why? Because there's something else that I didn't do, and that is that I didn't make sure that the output also was fast. So outputting large numbers to standard out also costs time. The way we fix that is as follows. Okay, so different ways to doing that, but I'm going to fix that by defining a new print writer that that is going to wrap standard output, but that will not flush lines. Okay, so let's see if that works. And then at the end, we'll flush that to make sure that that this appears. Let's try this. And see what happens now. And voila, the program runs. And it's 0.59 seconds. Okay, so out of 1 second time limit. So there is not much room if you program this in Java. So this is unfortunate, but those are things we know how to handle. I'm going to show you how to do this recursively um, in a second version of the program. So in this case, so first of all, the recursive version will use the same graph representation here, but the difference is that we don't use a DFS queue in this case. Okay, so we're still going to need a marked array, and I'm going to show this with a static function where this marked array basically will become a static variable. So this marked array um, will go here and will need to be declared there. But then we can only initialize it when we know what m is in this case. So here we're going to do a DFS, and we're going to start it with 0. We don't need a queue. We don't need to push on it. We probably also want to count the number of characters, number of nodes that are left, just for convenience. I'm going to lift that here to the top level as well. I'm going to set it before DFS is being called. So now what we have here in that body, this is what will be part of our DFS function. I'm going to start typing this here. Int u is the node that we are visiting, right? And so this code will then go into the DFS method here. So for each node u that we're visiting, okay, we're going through its neighbors. Oh, the neighbors, yeah, what about them? Well, these neighbors would then need to be lifted up here as well, or alternatively, you could also pass them in, okay? But for contest problems, I think it's perfectly fine to just lift them. Okay, so we need marked, we have left, marked, and here instead of pushing it, in this case, we perform recursive, a recursive call. Okay, let's see if that works. Okay, so that compiles. Should we test it? Sure, let's test it. Okay. Wrong, wrong clipboard. Let's just go ahead and submit it. Okay, so this is running. Seems to work, and voila, it works. And by the way, it basically the time didn't make a difference. Also 0.51 seconds. So whether this is done recursively or using an array deck data structure does not make much of a difference. Now, it could make a difference if the graph had many nodes, and this would result in large recursion depths. But in today's problem, with today's problem sizes, that is actually less likely to be the case. So typically they are designed to accommodate recursion. There are exceptions to that rule. So this was what I wanted to show you here. And hopefully you appreciate now why this problem was so easy for those who knew the trick. But this type of graph representation that is being shown here of these adjacency lists um, is a very, very, very common one. I want to point out one of the things that sometimes people forget is that when an edge is given, like AB here, that for an undirected graph, okay, for an undirected graph, um, you have to add them to both lists in this case. This is because in undirected graph, when you had 2, you could go to 3. When you had 3, you can go to 2. For directed graphs, that may not be the case. If you're here, you can go there, but not the other way around. But here, those are undirected graphs that we represent in this way.